Okay, so let's discuss more complex reactions than the simple two-component reaction. So to start off our discussion, let's just take one example that's just slightly more complex than before. So we're just going to say A plus B goes to 2C is our reaction of interest. And then if we wanted to write down, the free energy of the system, that would be equal to the chemical potential of A times the number of moles of A, plus the chemical potential of B times the number of moles of B, plus the chemical potential of C times the number of moles of C, right? And furthermore, we know that if initially the number of moles of A is equal to the number of moles of B, and that's equal to something we'll define as N0, then we know it will always be true that NA equals NB, right? Because whenever we use up an A, we use up a B. Whenever we gain an A, we gain a B. If we have a reverse reaction, right, we want to keep in mind we could have a reverse reaction. And so we can write down the number of moles of C, right, as being equal to 2 times N0 minus Na minus Nb, right? So if initially Na and Nb are both equal to N0 and there are no moles of C, then as the number of moles of A and number of moles of B go down, the number of moles of C goes up, right? So we're also assuming that initially we're going to assume NC equals 0. Okay, so that gives us this relation. Now that gives us a sort of simplified version of G we can write down just in terms of Na, right? So we can write that down as mu A plus mu B Na, since they'll both have the same number of moles and they'll be equal to the moles of Na, plus 2 mu C times N0 minus Na, right? And this gives us a way then to calculate our delta Rg, our rate of reaction of G, which would be equal to minus derivative of G with respect to Na at constant temperature and pressure. And we know that that will be equal to 0 in equilibrium. Okay. Okay, so so we can write this down. So what we get is that the condition for equilibrium is, so the condition for equilibrium is then, just let's take the derivative of this with respect to A. We get minus the derivative of this with respect to A. We get minus mu A minus mu B plus 2 mu C, right, is equal to 0. And that's our equilibrium condition. And then we also know that by definition, of the activity, mu A is equal to mu A theta plus RT natural log of the activity of A. And so we can write down this relationship between the chemical potentials in equilibrium in terms of the activities. So we get minus mu A theta minus RT natural log of AA minus mu B theta minus RT natural log of AB plus 2 mu C theta, let's put parentheses, minus RT natural log of AC. And that has to equal 0. And so what that tells us is that there's a relationship between these reference chemical potentials, so 2 mu c theta minus mu a theta minus mu b theta, must equal to minus RT natural log of AA times AB over AC squared. Right here I've just combined all the logarithms into one, and so this being then my right, this is my delta RG, right? So we can see that this is again my delta RG in equilibrium. So, well, this is my delta RG. And so, or my delta RG theta, right? Delta RG in the equilibrium or in the reference configuration, and that must be equal to minus RT natural log of K, where K is, again, my activity coefficient. And so we've got a very similar relationship, except that we can see the activity coefficient is related to activity of A times activity of B over activity of C squared. Okay, so that's a particular case, and we know that we could reduce those activities to be related to the partial pressures if we were in an ideal gas, but we don't necessarily know we're in an ideal gas, right? Okay, so now let's think in the general case. So in general, let's say we wanted to apply this to any reaction. So a general reaction we could write as minus nu A times A minus nu B times B goes to, and we could have any number of things on the left, to nu C times C plus nu D times D, where nu A, nu B, nu C, nu D are my stoichiometric coefficients. And notice that I'm just doing this in a very general sense. The ones that are on the left-hand side of the reaction, these are negative. Right? So if the stoichiometric coefficient is negative, it's on the left-hand side. If the stoichiometric coefficient is positive, it's on the right-hand side. And then I can write down any number of species with any number of stoichiometric coefficients, and I could write that down in a very general way, right? So if we were to analyze an equation like this, we could also get an expression for our delta RG, and that's going to be just like we did before. We're going to get delta RG theta plus RT natural log of, now we're going to call it Q. Q is our reaction quotient. And note that it's different than K in that K was our equilibrium constant, so the reaction quotient becomes the equilibrium constant at equilibrium. But we're not going to assume that we're at equilibrium yet, so Q is going to be a bit more general. And since we know we can write down our dG for this general reaction as mu C nu C d psi plus mu d nu d d psi plus mu A nu A d psi plus mu B nu B d psi, right? We can write this in general as the sum over all the participants in the reaction. So let's call that actually J of mu I nu I, or mu J nu J, all times d psi. And so our delta RG then is going to be equal to the derivative of G, with respect to C at constant temperature and pressure. So that's going to be just sum over J of mu J nu J, right? And we can further do the same kinds of tricks we did before if we note that mu J is equal to mu J in the reference configuration plus RT times the natural log of the activity coefficient of J in general. Then we know we can rewrite our delta RG as sum over J of mu J in the reference configuration times nu J plus RT times the sum over J of nu J natural log of AJ, right? And since this is a sum of logarithms, we can simplify that by saying that this is just sum of J, mu J theta nu J plus RT natural log of the product over all J of AJ to the nu J. Okay. And this gives us an expression for Q, right? So this must be Q, so Q for any general reaction is going to be equal to the product of AJ to the nu J. Okay. So that we can use then to find our equilibrium constant and for any general reaction. So if we were thinking about a particular case, so let's say we were thinking about ammonia, an ammonia reaction. So if we were to consider a case where we had nitrogen plus hydrogen going to ammonia, we could look up the difference in free energy between ammonia and elemental. So by convention, the free energy of elemental or the equilibrium elemental gases is 0. So we could look up the change in, or the free energy of formation of NH3, and we would get, we would, on a table, find 16.5 kilojoules per mole. So from that, we could calculate delta Rg theta, right, which would be twice that. So that would be minus 33 kilojoules per mole. And that would allow us to get, to calculate K, right, would be equal to the 33 kilojoules per mole over 2.48 kilojoules per mole for at equilibrium. So this is at 298 Kelvin. So this would give us an equilibrium constant, and from that we can get the ratios of the partial pressures if we're assuming these were all ideal gases. So that's just a particular use of this to get the partial pressures we would expect in equilibrium. Okay.